unusual setting for me. This is my first introduction to the world of nutrition sciences. So thank you all for sharing this opportunity with me. I am, as Manfred said, an air pollution exposure assessor and environmental epidemiologist. So I have never worked before in the area of thinking about combined effects of nutrition and air pollution. And my dear friend Fernando Holguin did such a beautiful job this morning in describing the health effects of air pollution. I'm kind of wondering what I can add to this story, but I'll do my best. If anything, I'm afraid I might complicate the story a little bit further. I apologize in advance. So let's go ahead and dive right into it. As Manfred said, my talk this morning is entitled Intra-Urban Variation in Air Pollution, Possible Implications for Nutritional Interventions. Intra-urban quite simply means within cities. So that's the scale of studies that I normally do, trying to understand how air pollution patterns within cities, and today we'll take that information to try to think about what that might mean for nutritional interventions towards alleviating some of the health effects of air pollution. So, as many of you have heard this morning, there's now a wide literature looking at the effects of multiple air pollutants, including fine particles, which we refer to as PM2.5, on cardiovascular, respiratory disease, as well as a wide range of other health outcomes. You were told this morning by Dr. Holguin that PM2.5 means little teeny tiny solid particles floating around in the atmosphere. They're not all round, but PM2.5 are the particles that act like they're smaller than 2.5 microns in diameter. Tiny little guys. And one of the important pieces to realize is that that's a physical measure. That's the physical size and the movement of a solid particle. But I'm a lot more interested in what is that particle? What is the chemical composition, excuse me, that makes up that particle, and how does it pattern across urban areas with, say, gaseous and other types of air pollutants? So air pollutants are a wildly complicated mix. It's a lot more than just one pollutant. So let's start to dig into that a little bit. So the health effects of air pollution varies tremendously within and between urban areas, varies by chemical composition, also varies by population susceptibility. Let's keep those factors in mind as we move forward. So this is a quick map of the country that I live in, and you'll notice that as you go from west to east, we have a funny little gradient in PM2.5 concentrations. We have generally, besides some pockets of California, generally lower PM2.5 concentrations across the west and then going higher in the east. Where I live right now is in Pittsburgh. It's that funny little dot right there. So obviously, concentrations in air pollution vary tremendously across space. Okay? We have a range here that goes from about 2 micrograms per meter cubed up to about 22 micrograms per meter cubed. That's an 11-fold difference on average across our country. Big variation in how much air pollution people are breathing in different places. Makes sense, right? Okay. It gets a little bit more complicated because within each one of our cities, there's a whole lot of variation that goes on at a fine scale. Now, this map here is taken from a study that I did in New York City. We ran 155 monitors in different locations across the city year-round for 2 years. And what we found is that there's extraordinary variation in how much air pollution people are breathing even within one city. So you'll notice here that there are generally higher concentrations in Manhattan and the inner parts of the city than there are in the further outskirts towards the suburbs, right? That makes sense, okay? This is the patterning in fine particles. This is similar to the patterning that we see in most primary combustion-related pollutants, including gases. So you'll hear these referred to as the nitrous oxide species. That's nitrogen dioxide, for example, or NOx species. Likewise for elemental carbon, other indicators of primary emissions from traffic, oil burning, what have you. This is opposite to the pattern that we see in other pollutants, such as ozone. That's a secondary pollutant that's formed as these chemicals start to mix in the atmosphere. If I were to show you our ozone map, it would be higher in the outer parts of the city, lower in the middle. Okay? So there are different types of air pollutants that are going on in different neighborhoods and in different cities. So the mix that individuals are breathing in different places is different. And that might matter for what's effective in thinking about which nutritional interventions are going to work in different places. Okay, There are, of course, studies of this type going on in various cities around the world, including my colleagues here in Europe have been running something called the ESCAPE study for the past 5 or 7 years or so. And what they are doing are running air monitors of the same type in a lot of different cities scattered across Europe and comparing those. And what you'll see here is a map comparing nitrogen dioxide across a lot of different European cities, and that's a nitrogen oxide map covered by the screenshot here. And what you'll see is that within each city, let's grab Lyon for example, there's a mean and there's a wide range, okay? There's Paris right above it. There's a mean and there's a wide range. And some of the bigger cities, here's Granada, lots of variation across that city. Makes sense, right? Big cities have really dense downtowns with a lot of sources going on, and they have the suburban areas where there's a little less activity. Some of the smaller cities might have a little bit less variability. The point is, there are differences in average concentrations across all these European cities. That's Barcelona up there, whoopsie. And there's a lot of variation within each one of these cities. And that's true no matter which pollutant you look at. Okay. Back to New York City and my study for just a second. Here's one of the key points that I want you to take away today, is that you've heard a lot about PM 2.5 health effects. Why do we study PM 2.5? Well, we're really good at measuring it. We have very well validated methods for capturing those physical little particles at this point. But you know what? It's an awful lot more expensive to look at the chemical composition of the fine particles. That's what I like to do. It's a lot more interesting to say what's going on in that particle, how is it chemically different from other particles, what might that mean for health. So in New York City, I dug into a whole lot of different elemental indicators or elemental components of fine particles, including nickel. Okay? Nickel is of great interest because it's been associated with neurocognitive effects, so brain outcomes, especially in kids. So people care a lot about nickel exposures. And guess what? We found higher concentrations of nickel in Manhattan and up in the Bronx than we did in other parts of the city. And does anybody know New York City well enough to know what that neighborhood is? Nope. Try again. Let me give you another hint. It includes the wealthiest census tracts in my country. It's the Upper East Side. Okay? The wealthiest part of our country has some of the highest air pollution in New York. People went crazy when this map was published. Okay? The reason why it's so high in that neighborhood is something called residual oil burning. So in New York City, huge buildings, very heavy old industrial boilers that heat these buildings, and they can handle the dirtiest, cruddiest leftover oil that you can buy. The cheap stuff that's full of heavy metals. So they're putting extraordinary amounts of heavy metals into the air in New York City, potentially leading to quite serious neurocognitive health outcomes. Now, you tell rich people that they're polluted, and oh my God, does policy change happen fast. The mayor, 1 year after this map was published, the mayor outlawed residual oil burning in New York City. Okay? That's now being entirely phased out. So there's no more number 4 and number 6 oil burning in New York. So we can have policy impact once in a while. Hallelujah. God bless public health. Okay. The important point, again, that I want you to take away is PM 2.5 is made up a lot of different types of chemical gunk. Why does that matter? Because all those different types of chemical gunk that are in fine particles have different effects on health. Okay? That could make a big difference for which types of nutritional interventions are effective. So right here, this work was done by my dear colleague Michelle Bell at Yale. She looked nationwide data. She got her hands on filter samples that were collected at all different cities across our country and analyzed those for chemical composition. Cost $300 a filter to do this, by the way. It's no cheap effort. But she looked at PM 2.5 effects on cardiovascular disease risk per interquartile range change in each one of these chemical components of fine particles. And likewise, she looked at the increased risk in respiratory disease per interquartile range, that's 25% to 75% range change in each one of these components of fine particles. And what you'll notice is that the most important species that came up on top for cardiovascular disease are not exactly the most important species that came up on top for respiratory disease. Both include some residual oil burning species. That's interesting. But there's a lot of components up here that are indicators for diesel exhaust, a couple indicators up here that are associated with things like brake and tire wear that come out of vehicular traffic on the roads every day. So different particles may matter differently for different health outcomes. Let's move on. I'm going to complicate this a little bit further. Sorry. So I'm currently doing a study in downtown Pittsburgh. So as some of you may be aware, yes, that's the city that Fernando and I live and work in right now. Relatively small city in the US. Probably about 300,000 people live in the city proper, about 1 million in the extended area. So not a big city by US size. But Pittsburgh has a proud history of being a steel town. Okay? So historically, we had a large number of steel power plants going, enormous amounts of pollution. As Fernando showed you today, they used to have to put the lights on, street lights on in the middle of the day so people could walk down the sidewalk safely. Okay? It's not like that anymore. It's quite a pretty city today. People like to say, air pollution problem, that's gone. Let's talk about something else. Well, not quite. There's no such thing as a clean atmosphere anymore. Sorry. In Pittsburgh, what we now have is a mix more similar to other American cities, other European cities, and other cities around the world, which means the variation in air pollution within your city, doesn't matter which one you live in, is probably driven by traffic. You might have a few unique industries that help to change the chemical mix in your city. Every city's got a little bit different mix, but traffic is a big one, okay? And that's common across most of our cities. And sure enough, that's what we're seeing in Pittsburgh today. So I'm running this study with the Allegheny County Health Department, that's our county, to understand the composition of fine particles in our downtown area. And they were particularly interested in indicators of diesel exhaust. Now this is a little more complicated because what I'm looking at here are the organic components of fine particles. These are volatile portions of fine particles. Sometimes they're produced from gaseous species transforming in the air in the presence of sunlight. Those reactions vary by temperature and humidity in the air, and they can form particles. Okay? So air pollution can move from gaseous to particle form. Rarely goes the other way. But a lot of those gases become that organic composition of fine particles that's very difficult to measure but can have really powerful health effects. And what we're seeing is even within this teeny tiny downtown area, we're probably talking 2 kilometers square. Even within that, we have huge variation in the concentrations of PM 2.5. So this range you probably can't see, it's a little fuddy, goes from about 9.9 micrograms per meter cubed up to over 21. So a twofold variation in concentrations, even in a tiny area. Likewise, we see lots of variation in elemental carbon, a common indicator of diesel exhaust. Lots of variation in benzoepyrene, that's one of our organic compounds, and likewise in hopanes, another organic indicator of diesel exhaust. So even in a small area of downtown in each one of your cities, lots of variation in how much pollution people are actually breathing. Sorry to complicate things. Okay, now I'm going to complicate things even further. The amount of air pollution that you're breathing varies by time of day, and it can vary dramatically by time of day, and that diurnal, which is our fancy word for within-day pattern, can vary a lot by city. So this is the diurnal pattern for nitrogen monoxide in Pittsburgh. Okay, we sort of see in the summertime, which is the lower curve, that's July, that's our summer, a peak around 6, 7 a.m. when vehicular traffic picks up, and then the sun comes out, it all transforms to ozone, and the NO burns off effectively. Okay, it's all chemically transformed. If you saw the curve on ozone, it would do exactly the opposite. Okay, and then during winter, that's a little bit more exemplified because we don't have as strong photochemical activity transforming all that stuff to ozone. So when I started a pilot study earlier this year in New Zealand, we took our monitors halfway around the world, went down to visit Lisa's part of the world, ran our monitors for a few weeks in Auckland and in Christchurch. We expected we'd see something similar, right? Wrong. In Christchurch, if you look at NO, it does something really unusual. We get this huge peak following that blue line there in the morning rush hour, and then it comes down, and then we get this huge peak happens again at 7 p.m. Huh, that's interesting. Nitrogen dioxide, a secondary compound which is formed directly from NO. It's a little more stable, so this is what you'll see more literature on. It's easier to measure, so more people will be working with NO2 people will be working with more. Kind of follows the same pattern, okay? A little bit less pronounced, but basically the same pattern. So what's going on? Why do these two cities have such a different pattern within the day? And therefore, why is the exposure pattern for individuals who live in these cities so different? Well, it's very simple. Tons of people in Christchurch use wood burning as their primary heat source, okay? There's a lot of damage in the buildings in Christchurch since the earthquakes 3 years ago. A lot of people still have damaged homes. A lot of the insurance companies have really been struggling to be able to help people get their homes fixed and back on their feet. A lot of people are burning a whole lot of wood to stay warm in a leaky home all winter. So you've got the traffic peak like you do in every other city in the world, and then everyone goes home at 7 p.m., boots up the wood burner. There you go. Thank you. Okay? That's a filter taking daytime. That's a filter taken nighttime in Christchurch. You can see the difference to the naked eye. 1 day's exposure. Day, night. Whoops. Okay, I'm going to make this a little bit more complicated. So not only does air pollution vary dramatically within cities, but susceptibility to air pollution varies dramatically within cities. There's a growing suite of literature in my field indicating that people of what we call lower socioeconomic position, okay, lower income people, may be more susceptible to the effects of air pollution. We don't exactly know why. Could be diet, could be education, could be nutritional factors, could be co-exposures, could be work-related exposures, a lot of different things. A strong hypothesis today is it might be the chronic stress of living a lower income life. Constantly worrying how you're going to pay rent next month, worrying how you're going to put the next meal on the table, worrying if you're going to lose your job, okay? In the US, in some cities, it might mean worrying if your kids are going to get home from school safe. So, those patterns in socioeconomic status vary a lot within cities, and as you might hypothesize, there's common patternings with air pollution, which in my field means, oh crud. How do we separate the health effects of air pollution from the health effects of poverty or susceptibility when those might be affecting the same populations? It's a really hard question to answer in the epidemiology. So we're starting to tear that question apart a little bit more. There's growing evidence, as I said, that lower SEP might be making people more susceptible, and there's this hypothesis that chronic stress might be one important cause. The reason I raise this example is to help us think a little bit more clearly between the difference in high air pollution exposure versus high susceptibility to air pollution. They're two very distinct concepts, and it's important to keep them clear, because from a nutritional intervention standpoint, it says, do we want to intervene where people are highly exposed to air pollution, or do we want to intervene where people are highly susceptible to air pollution? Two different questions, and it's careful to think about what is the intervention you're designing. Okay. So some stressors are very tightly correlated. That means they occur in the same spaces with air pollution. Traffic's my favorite example. Traffic-related air pollution is high in the same places where traffic-related noise is high. If you have higher rates of hypertension among people living alongside a major road, is it the air pollution? Is it the noise? Hard question to answer. Okay? And chronic stress is associated with a whole lot of changes in immune, endocrine, metabolic function, a lot of reasons we might believe that it would affect susceptibility. So this story is starting to come together, and nutrition is probably one piece of it, and it's challenging for us to think about, is it working, again, more on buffering exposures or changing susceptibility patterns? This is a study I did a few years ago and published in 2007, and I show it to you as an example of one cohort growing up in the East Boston neighborhood, in my home city of Boston, living in the vicinity of Logan Airport. And what we were able to do is to build a model estimating nitrogen dioxide exposure at all of these children's homes. And these children had been followed from the time that they were born by the East Boston Medical Center through about age 14 or so. And what we found in this cohort, after estimating NO2 at every child's home, positing importantly that NO2 here is just a proxy for primary traffic-related pollution, okay? Not necessarily the driver, but it's saying that whole vehicle mix is higher at some kids' homes versus others. And then looking into the epi, adjusting for everything else we could in this cohort, such as mothers smoking, education, the child's sex, the child's age, a main effect for exposure to violence, a very important stressor in American cities. We found that when we dichotomized our group by children who had above median versus below median exposure to violence, we found that the entire association between nitrogen dioxide and asthma etiology or asthma diagnosis was explained among those children with high exposure to violence. That's interesting. Okay? So there might be something here helping us to tear apart what underlies susceptibility patterns, and when we look at associations between air pollution and health outcomes, who might be the susceptible populations? Who do we want to identify and intervene with first? Okay. Now, of course, the first question is, well, what is that a proxy for? Is it really exposure to violence? Is it really stress? Or is it standing in place of something else? Diet, education, what have you. So, sure enough, we got some rats. Okay? We stressed out our rats, or we stressed half of our rats. This is how. We took the little guy, that's our test rat, we put him into the cage of a larger dominant male, and he fought for his life 20 minutes a day on alternating days over the course of 5 weeks. Okay? I know, it's incredibly rude. But we'll do some experiments on rats if it helps improve health outcomes in kids. That's the trade-off we have to make in our world, okay, in our research world. And then on the odd days, we put these little guys into a concentrated air pollution chamber. So I'm pulling ambient air in from Boston, concentrating the particles in it 30 times and delivering it to my rats. The important thing here is that all of my rats are getting the exact same air pollution exposure. And I can control how much air pollution exposure they get. Okay? That's the really brilliant aspect of this system. And sure enough, what you'll see is that we found changes in respiratory function associated with changes in fine particle exposure. But here's the trick. If you compare a non-stressed rat in white to a stressed rat in black, you'll see that the stressed rat, in response to the same 1 standard deviation increase in fine particles, has a significantly higher respiratory frequency, significantly lower peak inspiratory flow, significantly lower peak expiratory flow, significantly lower tidal volume, significantly lower minute volume. Oh my goodness. Okay, we're really starting to get somewhere in understanding susceptibility to pollution now. So, let's go ahead and wrap up. So, my key point today is that in order to think clearly about nutritional interventions or other interventions towards reducing the health effects of air pollution, we really might have to start by understanding our pollutant mix more clearly, understanding both the particles and gases and what's high in your city and in different parts of your city. We need to tear apart that chemical composition of PM 2.5 because it's not all the same, not remotely, not by a mile. Okay? And we need to understand those susceptibility patterns and think clearly about, are we intervening in places where pollution is high, or are we intervening in places where susceptibility is high? Two totally different concepts. Okay? What key outcomes would we start with? Well, gee, PM 2.5 has been associated with asthma and a whole suite of respiratory outcomes. It's been associated with cardiovascular disease, been associated with neurocognitive outcomes, a lot of places we could start. Okay? Might have to start simple, work our way up. Respiratory disease is often a starting point because, hey, when you inhale, the lungs and the alveoli is the first place it hits. Okay, so we may need to think about the pathways, the physiological pathways through which these many different air pollutants and also stressors may be impacting health. A good place to start might be inflammation. Okay, many different pollutants and stressors work through inflammatory pathways. If that's a place that we can intervene and buffer some inflammatory effects, maybe there's a common pathway to start with. And then finally, keep in mind that spatial variation, the timing of your exposures, and the physiological impacts that different types of pollutants may have as you're thinking about designing interventions. So I will wrap up. I'd like to acknowledge DSM, Manfred, Celine, all of the people who did an extraordinary job to get us over here. Certainly to all of my funders, to my collaborators, in particular Fernando at the back, who got me tied in with this wonderful group, and of course all of the people back in my lab who do the real work. Okay? So with that, thank you very much.
Thank you very much. Excellent presentation. Thank you.
Thank you.
Oh, thank you very much for your wonderful talk. I really appreciate that. I can understand, yes, there is a need to have a nutritional intervention because the reality is we have air polluted already. But my question to you as an expert in air pollution, how we can stop more air pollution?
That is the million-dollar question, isn't it? And I'm glad you asked. I'm glad you asked. Because to be completely honest, we could probably improve the diet of the vast majority of people on the planet. We could reduce stress of the vast majority of people on the planet, hypothetically speaking, right? We could do all of these things to make people less susceptible, and we would probably not remove all the health effects of air pollution. Air pollution's not going away. There's tons of it. It's everywhere in the world now, okay? And people are all going to be differently susceptible, but as long as it's there, it's going to be impacting someone. The obvious answer is that we need to be working at two levels. So one is supporting changes such as regulatory changes, improvements in technologies, development of other energy sources, improvements in vehicular technology, getting people out of cars and onto public transportation and bikes more often. Obviously, reduce as much air pollution as we can, okay? And at the same time, think about improving everybody else's baseline health status, including nutrition, stress, et cetera, to help the population be less susceptible. It has to be a two-tiered approach.
Thank you.